So, we are starting a new chapter on electrodynamics. And this is the electromagnetic induction. Then, as far as this electromagnetic induction is concerned, we have to study what is the Ohm's law in electrodynamics. In ordinary current electricity, we have studied the Ohm's law as R is equal to V by I. But here, the Ohm's law in electrodynamics is J equal to sigma E. And to study this law, J equal to sigma E, we have to get some idea about the volume current density J. Volume current density J is equal to dI by dA perpendicular. So, what is dI? dI is the element of current flowing in this direction. So, this current is facing an area D which is perpendicular to the flow of current. That is why this area is called dA perpendicular. So, the element of current flowing dI divided by the area facing the current, perpendicular area facing the current, dA perpendicular, that is J. So, it is actually the current per unit area, So, its unit becomes ampere per meter square, current per unit area. And this current density J is proportional to the force per unit charge. Force per unit charge. As you know, there is an electromagnetic force. So, force per unit charge, F, it is directly proportional to the J. So, to remove this proportional sign, we have to add a constant here. That constant is sigma. Sigma, the constant is called conductivity of medium. Conductivity of medium. This is F is force per unit charge. The unit of J is ampere per meter square. And sigma, by adding sigma, this equation becomes J equal to sigma F. When sigma becomes infinity, the conductor becomes a perfect conductor. Sigma becomes infinity means perfect conductor. The complete current is flowing. There is no resistivity. And the reciprocal of sigma is the resistivity, rho. And the rho is having the unit is ohm meter. Ohm meter is the unit. So, what is the unit of conductivity? Ohm inverse, meter inverse. Ohm inverse, meter inverse will be the unit of conductivity. And the force exerted per unit charge, F, is an electromagnetic force. So, this F, force per unit charge, F, is an electromagnetic force. And this force is defined by Lorentz law. The total Lorentz force. It is a combination of the electric Lorentz force plus magnetic Lorentz force. Here we are assuming Q equal to 1. Electric Lorentz force is QE, magnetic Lorentz force is Q into V cross B. If you put Q equal to 1, the equation becomes this one. Why we are taking Q equal to 1? We are considering unit charge. That is per unit charge. That is why we are taking it as unit charge. And also, the quantity V, it is very small. So, this term can be neglected. So, only this term arises. So, this term arises means F becomes, in this equation, F becomes E. So, equation 1 gives J equal to sigma E. And this equation J equal to sigma E is called the Ohm's law in electrodynamics. Ohm's law in electrodynamics. So, can you reproduce this? Now, let us consider what is meant by electromotive force. We know for an electrostatic field, closed line integral E dot dl equal to 0. And also, we know that current through a conductor is I equal to surface integral J dot dA. This is derived from this equation. J is equal to current by area. So, current is equal to J into area. But here, J, we can substitute by Ohm's law. Ohm's law in electrodynamics is J equal to sigma E. Substituting in this equation, we get I equal to surface integral sigma E dot dA. That is equation number 2. Purely, electrostatic field E cannot cause a current to circulate in a closed path. Why? This is the answer for that. This equation is the answer for that. To maintain current, in addition to electrostatic field, an external source of energy or source of force Fs is needed. What are the external source of energy? Battery, connecting a battery, then or a current generator, a solar cell, thermocouple, etc. are external source of force. So, by adding this external source, the total force F becomes Fs, this Fs, plus E. E is the electrostatic force, electric field. So, taking line integral F dot dl is equal to RHS also U dot dl. But in the open circuit, E becomes 0. E becomes 0 means RHS becomes closed line integral Fs dot. So, E is equal to integral Fs dot dl. This E is called the electromotive force or EMF of the circuit. Actually, E is the work done per unit charge. E is the work done per unit charge. Work done per unit charge. So, W is equal to work done per unit charge. That is actually E. So, what will be its unit? Its units will be work done means joule per coulomb. Joule per coulomb. Okay. Then E determines how much current will flow in the circuit. If E is large, then current will be also large. So next line we can argue that E is equal to closed line integral F dot dl. What is F? F is equal to J by sigma. Why? J is equal to sigma F. So, F is equal to J by sigma. So, what is J? J is equal to I by A, current by area. So, instead of this J, we are writing I by A. So, we are getting closed line integral I by A sigma dl. You bring this current constant outside the integral sign. So, I is equal to line integral 1 by A sigma dl. So, what is this? This is the resistance R. Where R is the, so this becomes IR, where R is the total resistance of the loop. And EE is IR. E is equal to IR. So, this is also another relation for the electromotive force. Another relation for electromotive force. Now we consider what is meant by torsional EMF. For this, you just consider this black box represents a uniform magnetic field. it represent B. It is represented by B, uniform magnetic field. So this arrow indicates that the magnetic field is acting towards the surface of the board, towards the plane of the board. In this magnetic field here, we are having a wire, and here for an LED bulb is connected here with resistance R. And this wire, this ABCD section of the wire is inside the magnetic field, and it is pulled towards right with a velocity v. So what happens? So an EMF is induced in the wire. Due to this EMF, this wire, this bulb will glow, which shows that a current is flowing in the circuit in the clockwise direction. So an EMF is generated, and this EMF E is closed line integral F magnetic into dl. So what is F magnetic? F magnetic is F by Q. F by Q. So what is F? F can be derived as F is equal to Q into V cross B. That is magnetic Lorentz force. And these two are perpendicular to each other. B is in this direction, V is in this direction. So the angle between V and B is 90 degree. So this is QVB sin 90 equal to 1. So it becomes QVB. So F is equal to QVB, that is QVB by Q into dl. Q and Q are getting cancelled. So VB closed line integral dl. What is closed line integral dl? This distance AB, what is it? It is h. So it is VBH. So we got the motional EMF epsilon E equal to VBH. Motional EMF E equal to VBH, where V is the velocity with which the conductor is moved towards right, and B is the magnetic field acting perpendicular to the plane, and H is the length of the. Now we have to discuss about the flux rule in electromagnetic induction. So here you just consider a small area, and through this area the magnetic field is passing. D represents the magnetic field. N is the normal to the plane. That is, N is acting in this direction, normal to the plane. Actually, we know magnetic flux is equal to phi is equal to B dot D, or d phi equal to B dot D, or phi equal to B dot A. And the unit of phi in SI unit, it is Tesla meter square or Weber. 1 Weber is 10 raised to 8 Maxwell. Maxwell is the CGS unit of flux. And so from this equation we can write d phi equal to B dot dA. Then phi is equal to surface integral B dot dA. What is dA? dA in the previous figure, we know that h is the length of the conductor and s is the distance through which the conductor is moved. So area covered is equal to dA is equal to hs. So instead of this dA, I am writing hs. And here b is constant, so b is taken outside the integral side. So in the previous figure, not this previous, last figure, last but one. So in that figure, when the loop moves towards right, the area decreases. But the moment is just like this, so the area covered decreases. So what happens to this equation? So when time increases, s decreases. S means distance decreases. So this is phi. I am differentiating this phi as d phi by dt equal to bh into ds by dt. I am talking about this ds by dt, which is the velocity v. In this ds by dt, when time increases, the distance s decreases. That is, if it is moving just like this, when time increases, the distance s also decreases. So when time increases, distance decreases. So ds by dt is taken as negative. So what happens to this equation? So this equation changes to d phi by dt equal to minus bhv, minus bhv. We already found that bhv is emf. So this is equal to minus e. So finally we are getting the equation E equal to minus d phi by dt. E is equal to minus d phi by dt. This is the flux rule for motional EMF. Now we have to study two important theorems. First one is the Stokes theorem. According to Stokes theorem, the surface integral del cross a vector v dot dA can be written as line integral vector v dot dA. And second one is the Gauss's divergence theorem. Gauss's divergence theorem. It is also known as the Green's theorem. And Gauss's divergence theorem is the volume integral of del dot a vector d term, it is equal to surface integral of vector dot d. Surface integral of vector dot d. So these two theorems are very important in electrodynamics. So here V, what is V? V stands for a vector, any vector. And del is an operator, dA area, this is area, and this is a length. So by using Stokes theorems, surface integral can be converted into line integral. Surface integral can be converted into line integral, or line integral can be converted into surface integral by using Stokes theorem. By using Gauss's theorem, Gauss's divergence theorem, the volume integral can be converted into surface integral, or surface integral can be converted into volume integral. Here also V denotes a vector, any vector, any vector. D2 means volume, dA means area. So these two theorems are very important in the case of electrodynamics. So let us consider the electromagnetic induction and Faraday's law. The famous law in electromagnetic induction is Faraday's law. So here we have studied that the EMF produced is rate of change of phi. E is equal to minus d phi by dt. That is equation number 1. That is, a changing magnetic field induces an electric field. Change in magnetic field produces an electric field. This equation E equal to line integral E dot dl, that also we have studied the equation. From these two equations 1 and 2, we can write this closed line integral E dot dl is equal to minus d phi by dt, and which is the EMF E. So you just see this figure. This is the current element, and dl is the current element dl, and this is an area dA. This area dA, small area is considered this area dA, and this dA is perpendicular, dA vector dA is perpendicular to the area surface dA, B is also perpendicular. Then magnetic flux phi through the closed path can be written as phi is equal to closed surface integral B dot dA. That is equation 4, substituting this 4 in 3 in this equation. So closed line integral E dot dl equal to d by dt of phi. That is minus d by dt of phi means B dot dA is substituted here. So if the closed path is kept stationary, we are not moving this closed path, it is kept stationary. So this time derivative can be put inside the integral sign. And now this time derivative, this becomes a partial derivative, dou by dou t. So this equation changes to a new form, line integral E dot dl is equal to minus dou b by dou t dot dA. This represents the integral form of Faraday's law. This represents the integral form of Faraday's law. And so this is the integral form of Faraday's law. Then you apply Stokes' theorem, which converts line integral to surface integral to LHS. LHS means this one, closed line integral E dot dl. It transforms to surface integral del cross E dot dE. Substituting for this E dot dl from this, what happens? Surface integral, this equation becomes 6 becomes surface integral del cross E dot dE equal to minus of surface integral dou b by dou t dE. So we are getting this relation. From this you can argue that this del cross E is equal to minus dou b by dou t. This is the differential form of Faraday's law. This is the differential form of Faraday's law. Differential form of Faraday's law. So we got two expressions. First one is the equation 6 is the integral form of Faraday's law, and the last equation del cross E is equal to minus dou b by dou t is the differential form of Faraday's law. Del cross E is equal to minus dou b by dou t. It is the differential form of Faraday's law. The negative sign is explained by Lenz's law. This is a differential form of Faraday's law. Del cross E equal to minus dou b by dou t. So by varying magnetic field B, an electric field E can be produced. So we know that E is not a conservative field since del cross E is equal to 0. Mathematically, we know that div of curl equal to 0. Del cross E is curl of E. Div of del cross E means del dot del cross E, which is equal to minus dou by dou t of del dot B, which becomes 0. From this step, we conclude that del dot B is equal to 0. That is, magnetic field will not diverge. It will curl. You see two important relations. The first one is Faraday's law, and the second one is Ampere's law. Faraday's law, differential form of Faraday's law, del cross E is equal to minus dou B by dou t. And Ampere's law is del cross B equal to mu 0 J. And here, in this Ampere's law, there is some discrepancy in this Ampere's law, and Maxwell corrected this Ampere's law into a new form, and then those equation is known as Maxwell equation, which we will study later.
Now,
we have to discuss about this inductance. In that, first of all, self-inductance. So, as you have studied this self-inductance of a coil, you just consider this is self-inductance of the coil. Then you just consider the make and break arrangement of this circuit. Actually, this is a tap key. When tap key is pressed, current increases from 0 to maximum, and when it is released, then current decreases from maximum to 0. So when a current is passing in this inductor L, an EMF is induced in this coil, and that EMF is called the induced EMF, and the induced EMF is just opposite to the applied EMF. And when current in a coil grows, maximum flux also grows. That is, flux means the maximum flux also grows. And when current decreases, that is from maximum to 0, the flux also decreases. This change in magnetic flux produces an induced EMF in the coil, which opposes the decaying current. If the decaying current is in this direction, induced EMF will be in the opposite direction. So, the current developed by the make and break arrangement in the coil and the flux produced is related by this relation, that is phi proportional to I. And to remove this proportional sign, we have to add a constant, and that constant is L, where L is called the self-inductance of the coil, and its unit is Henry. Unit is Henry. So we can write phi is equal to Li. We already got this equation, E is equal to minus d phi by dt. Instead of phi, you substitute Li, so minus d by dt of Li. You bring the constant outside the differential, then L minus L into di by dt. So we got the final expression, E is equal to minus L into di by dt. So imagine a steady current. We are discussing about the energy in magnetic field. And imagine steady current. Steady current means this is the steady current. And a sudden switching of this switch, current increases from 0 to maximum. So the field, magnetic field, increases from 0 to maximum. So an EMF is induced. And this EMF causes the current source to do work. So the current source, it forces the current source to do work, and that is the energy produced in magnetic field. We know dW by dt is equal to minus EI. You just remember power is equal to EI. So what is the meaning of this negative sign? Negative sign shows that work is done against EMF. This work is done against EMF. So in opposite direction. Also, we have derived that E is equal to minus L di by dt. So dW by dt is equal to minus. Instead of E, you can substitute this. So this minus L into di by dt into I. That is equation 2. Minus into minus plus. So L into I into di by dt. So W equal to integral 0 to L Li di by dt into dt. Is that correct? This is dW integral. dW becomes W, then dt. Then bring the L outside the integral sign. So L 0 to I I di by dt. So this is equal to half Li square. Half Li square. Integrating, we are getting this result. Half Li square. So W is equal to half Li square is the energy. Then we consider about the magnetic flux phi. By definition, it is surface integral B dot dA. And B, in terms of vector potential A, we can write this B equal to del cross A. So instead of B, here substitute del cross A. So del cross A dot dA. Using Stokes theorem here, surface integral can be converted into the line integral. So phi is equal to line integral A dot dA. So phi also, we know that phi is equal to Li. So substituting this phi is equal to Li here. So you are getting Li equal to closed line integral A dot dA. Then substitute the value of Li in equation 3 here. Here W is equal to half Li square, can be plus half Li into I. So instead of this Li is substituted. So you are getting half I into closed line integral A dot dl, which is equal to W is equal to half closed line integral A dot I dl. This is the energy produced in the magnetic field. So now let us consider one more thing. By considering the volume current, the above equation can be written as W equal to half volume integral A dot J dt. That is equation 4. And we have studied from Ampere's law that cross B is equal to mu 0 J. Substituting this result in equation number 4, we get W equal to half volume integral A dot J. Instead of J, you write instead of J equal to del cross B by mu 0. So substituting for J, del cross B by mu 0 into d2. So half 1 by 2, bring this mu 0 outside, integral sign, 1 by 2 mu 0 integral A dot del cross B d2. From mathematics, we have the vector identity del dot A cross B is equal to B dot del cross A minus A dot del cross B. A is the vector potential and B is the magnetic field. And we know del cross A is B. Del cross A is B. Then from this relation, A dot del cross B can be written as B square minus del dot A cross B. Then substituting for this term in this equation here, what you get? W equal to 1 by 2 mu 0 integral B square into d2 B square d2 minus then again integral, volume integral, then del dot A cross B into d2. So this becomes, so here this is the volume integral. By using Gauss's divergence theorem, we are converting this integral into the surface integral. So this is the surface integral. So this term changes to del dot A cross B d2 volume integral volume integral del dot A cross B d2 can be changed into surface integral A cross B dot d using Gauss's divergence theorem. Now W becomes in this form. Equation 5. The integration in equation 4, you just see this integration. It is entire volume integral. So this is an all space integral. So here the importance is for the volume integral, not for the surface integral. So we are neglecting this surface integral because its importance is very less. So larger the region we select, greater is the contribution from volume integral, and smaller due to surface integral, we are taking this part only. So finally, the energies equation, the magnetic field energy equation becomes W equal to 1 by 2 mu 0 all space integral B square d2, B square